Imagine this. It's a crisp night in early July 2025, and astronomers at the Atlas Survey Telescope in Chile are sifting through routine data, hunting for potential threats from space. What they stumble upon isn't a near-Earth asteroid or a routine comet. It's something far more extraordinary. A visitor from the stars hurtling toward our solar system at an unimaginable speed, defying the gravitational pull of our sun. This is 3I/ATLAS, the third confirmed interstellar object ever detected, named for the ATLAS system that spotted it on July 1st, 2025. In the weeks that follow, the world's most advanced telescopes turn their gaze skyward, but it's not until NASA's James Webb Space Telescope locks on that the real revelations begin. Fast forward to today, October 3rd, 2025, and this cosmic wanderer is zipping past Mars, mere hours from its closest brush with the red planet at about 30 million kilometers away. Right now, as you're watching this, 3I/ATLAS is racing at over 130,000 miles per hour, fast enough to cross the entire United States in under 2 minutes. But speed alone isn't what's gripping the scientific community. No, it's the anomalies, the patterns that don't fit, uncovered not by human eyes, but by a groundbreaking fusion of quantum computing and artificial intelligence. Stick with me through this video, because by the end, you'll see why this isn't just a comet. It's a portal to rethinking everything we know about the universe. And trust me, the twists get wilder the deeper we go. Hit that like button if you're ready to dive in, and subscribe so you don't miss the updates as this story unfolds in real time. Let's set the stage properly, because understanding 3I/ATLAS starts with its dramatic entrance. Discovered just 3 months ago, this interstellar comet, officially dubbed C/2025 N1 Atlas, or simply 3I for short, emerged from the direction of Sagittarius, already deep inside Jupiter's orbit at about 410 million miles from the Sun when first spotted. Unlike the comets born in our solar system, which loop obediently around the Sun like loyal pets, 3I/ATLAS is on a one-way hyperbolic trajectory. It's not orbiting, it's slingshotting through, a fleeting guest from another stellar neighborhood, destined to exit our cosmic backyard forever after its closest solar approach on October 30th, 2025. Picture it, an icy nucleus, estimated by Hubble's sharp eye to span anywhere from 1,444 feet to a whopping 3.5 miles across, wrapped in a hazy coma of gas and dust that's starting to brighten as solar heat awakens its frozen secrets. Pre-discovery images from late June, pulled from archives like Caltech's Zwicky Transient Facility, show it as a faint streak against the stars. But now it's alive, active, and under constant surveillance. As of this very moment on October 3rd, 2025, 3I/ATLAS is making its grand flyby of Mars. At 4 UTC today, that's 11 p.m. CDT last night for those in the central U.S., it reaches its nearest point to the red planet, a cosmic close encounter that's got mission control buzzing. NASA's Mars Reconnaissance Orbiter, the Perseverance and Curiosity rovers, ESA's Mars Express and ExoMars Trace Gas Orbiter, even China's Tianwen-1, and the UAE's Hope probe, they're all turning their instruments toward this intruder, capturing data on its composition, its glow, its influence on the thin Martian atmosphere. Imagine the scene, dust devils swirling on Mars' surface below, while high above, a relic from another star system streaks by at 219,000 kilometers per hour, its tail beginning to unfurl like a banner announcing its arrival. And that's just the appetizer. Later this month, as it hurtles toward perihelion, that magic moment when it's closest to the Sun at 1.4 astronomical units, or about 130 million miles, it'll pass suspiciously close to Jupiter, Venus, and even brush the edges of our inner solar system. No danger to Earth, mind you. Its nearest pass to us is a safe 1.8 astronomical units away. But the implications, they're stratospheric. Why does this matter so much? Because interstellar objects like 3I/ATLAS are rare cosmic messengers. Only two have come before. The enigmatic Oumuamua in 2017, that cigar-shaped oddity that accelerated inexplicably, sparking debates about natural gas jets versus, well, something more exotic. And 2I/Borisov in 2019, a more straightforward comet with familiar chemistry, but still a thrilling outsider. Now with 3I/ATLAS, we're at 3 and 8 years. Statisticians are recalculating. These visitors might be more common than we thought, perhaps one every few years if we keep our eyes peeled. Each one carries snapshots of distant star systems, chemistry forged in the nurseries of other suns, physics tested over light years of travel. But 3I/ATLAS. It's not just whispering secrets, it's shouting them. And the tool that's amplifying those shouts? Quantum AI, the bleeding edge tech that's turning raw telescope data into mind-bending predictions. But before we unpack the anomalies that have scientists losing sleep, let's demystify what quantum AI even is and why it's revolutionizing astronomy right now. Quantum computing isn't your grandpa's supercomputer. Classical computers, the ones powering your laptop or even NASA's Cray systems, process information in bits, zeros or ones like flipping a coin one at a time. They're linear, sequential, great for straightforward tasks, but woefully inadequate for the chaotic ballet of interstellar dynamics. Modeling how a comet's ices sublimate under solar heat, how magnetic fields twist its tail across millions of miles, or how dust particles interact with solar wind. That could take centuries on classical hardware, churning through equations one by one. Enter quantum computers. They use qubits, which can exist in multiple states simultaneously, 0, 1, or both at once, thanks to the weird magic of superposition and entanglement. It's like flipping a trillion coins all at once and seeing every possible outcome in parallel. Suddenly, those centuries-long simulations, they're done in seconds. NASA's Quantum Artificial Intelligence Laboratory, QUAIL, tucked away at Ames Research Center, has been pioneering this for years, but 2025 marks a tipping point. In July, they hosted the Science Mission Directorate's Quantum Technology Day, bringing together experts to brainstorm applications from exoplanet detection to trajectory optimization for deep space missions. Google's Sycamore processor, which shattered records in 2019 by achieving quantum supremacy, has evolved into full-scale systems capable of error-corrected computations. IBM's quantum network, now with over 100 partners, is pushing hybrid quantum classical algorithms that blend the best of both worlds. And in space exploration? A February 2025 report from the Quantum Insider highlighted how these systems are slashing interplanetary mission planning time by up to 90%, simulating resource allocation for Mars habitats or asteroid mining with unprecedented fidelity. But for 3I/ATLAS, it's not just planning, it's prediction. When terabytes of data from Webb's near-infrared spectrograph poured in after its August 6th observation, classical AI models crunched the numbers and spat out, "Comet, probably." Quantum AI, it ran millions of parallel scenarios and uncovered layers of complexity no one anticipated. The result? 3 glaring anomalies that challenge our textbooks. Let's break them down one by one and see why they're sending ripples through the astronomical community. Anomaly number 1, the carbon dioxide conundrum. Comets are the solar system's time capsules, frozen relics from 4.6 billion years ago when our nebula cooled into planets. Typically, they're water-rich, about 80% ice by mass, with water sublimating first as they warm near the sun, birthing the iconic coma tail. Think Halley's Comet or Hale-Bopp, bright, watery spectacles that light up our skies every few decades or centuries. But 3I/ATLAS? Webb's spectra revealed a gas coma dominated by carbon dioxide, CO2 levels far exceeding water vapor, alongside traces of carbon monoxide, CO, and even the sulfurous carbonyl sulfide, OCS. An Archive preprint from August 25, 2025, detailed the findings. At a heliocentric distance of 3.32 astronomical units during observation, the CO2 emission was so pronounced it suggested an 8-to-1 ratio over water in the outgassing process. That's not unusual. That's unprecedented. To grasp the impact, consider the implications for formation. Our solar system's comets formed in a water-dominated disk around a young sun, where hydrogen and oxygen bonded readily into H2O. But if 3I/ATLAS is pumping out CO2 like a cosmic soda fountain, it likely gestated around a star with wildly different chemistry, perhaps a carbon-rich red dwarf, where carbon monoxide and dioxide were the building blocks of ices. Quantum AI simulations fed this data, modeled over 50,000 stellar nurseries, predicting origins in environments 10 to 20 light-years away, near systems like TRAPPIST-1 or Proxima Centauri. Why does this matter? Beyond the science, CO2 dominance could hint at exotic volatiles that, if harvested, might revolutionize propulsion tech. Imagine thrusters fueled by interstellar ices, more efficient than chemical rockets. But it's the why that hooks you. What kind of stellar forge could invert the ice chemistry we take for granted? The AI's outputs aren't conclusive, but they whisper of a universe far more diverse than our backyard. And as 3I/ATLAS nears the sun, expect that CO2 tail to flare brighter, revealing even more. Don't go anywhere. The next anomaly ups the ante. Now let's talk metals, specifically the bizarre case of nickel without its iron sidekick. In stellar nucleosynthesis, the universe's atomic kitchen, iron and nickel are forged together in the crushing hearts of massive stars. Iron 56 is the most stable nucleus, and nickel 62 nips at its heels. They co-emerge in supernovae blasts, hitchhiking through space as inseparable partners in cosmic dust and planetesimals. Every meteorite we've ever analyzed, every comet in our Oort cloud, shows them bonded, iron-nickel alloys that pepper planetary cores and asteroid belts. It's basic astrophysics. You don't get one without the other. Or so we thought. Enter 3I/ATLAS. Spectral lines from ground-based observatories like the European Very Large Telescope's UVES instrument, combined with Webb's infrared gaze, detected strong nickel absorption in the comet's dust cloud. Clear signatures of Ni emissions, but iron, virtually absent. A September 2025 Archive paper flagged this as extreme nickel production, with the comet belching out metallic vapors at rates 100 times higher than typical comets, yet no corresponding iron spike. Quantum AI took this puzzle and ran with it, simulating fractionation processes, how particles separate in space, across millions of scenarios. The verdict: this nickel isolation demands hyperspecific conditions, perhaps formation in a supernova, remnant with asymmetric ejection, flinging nickel-rich ejecta light-years away while iron clumped elsewhere. Or more intriguingly, post-formation processing, like collisions in a debris disk that preferentially stripped iron, leaving a nickel-heavy core. Harvard astrophysicist Avi Loeb, no stranger to bold ideas, penned a Medium post just days ago calling this new data on the extreme nickel production, suggesting it could stem from a metal-poor parent star where nickel pathways dominated. But the quantum models go further. They predict the comet's nucleus harbors a metallic fraction up to 5% by mass, way higher than the 0.1% in solar system comets, implying it's not just icy, but laced with a bizarre alloy we can't replicate on Earth. Imagine mining this for next-gen batteries or superconductors. The applications boggle the mind, yet the unease creeps in. How does a natural object achieve such purity? Is it a fluke of cosmic chance or evidence of selective enrichment in an alien forge? As probes like Psyche, ironically en route to a metal asteroid, snap photos during its September 4th flyby, we're getting closer to answers. But hold tight. The third anomaly ties it all together in ways that feel almost intentional. If the chemistry anomalies were eyebrow raisers, the trajectory is a full-on jaw-dropper. Comets don't fly straight. They tumble, outgas, and nudge themselves via non-gravitational forces. Oumuamua taught us that in 2017, its weird acceleration, explained mostly by hydrogen outgassing, but debated to this day, 3I/ATLAS question mark. It's echoing that mystery, but with a twist. Quantum simulations, processing Webb and Hubble data, detected slight deviations from pure gravitational paths. Tiny accelerations, about 10 to the minus 6 meters per second squared, not fully accounted for by solar gravity or radiation pressure. Worse, they're lateral, sideways shoves, not the expected radial push from solar wind. An IFL Science article from late September dubbed it a major anomaly, linking it to uneven jetting from the CO2-rich surface. But here's the kicker. The AI ran 50,000 jet configurations, random bursts, rotational spins, thermal lags, and none match perfectly. The forces are too consistent, too precise, like a balloon twisting in a controlled spiral rather than random gusts. Weighing in at an estimated 33 billion tons, 3 to 5 orders of magnitude heavier than Oumuamua or Borisov, this beast's mass amplifies the puzzle. Quantum models suggest the acceleration stems from asymmetric outgassing, perhaps amplified by that nickel-laden dust acting as a catalyst for exotic reactions. But gaps remain, 5 to 10% unexplained variance in the path, per the simulations. Is it just undiscovered physics, CO2 jets behaving differently in interstellar vacuum, or something engineered, a relic steering subtly toward our system? The AI doesn't claim artificiality, it highlights the mismatch. A.V. Loeb again. Anomalies like these leave open possibilities we can't ignore. As JUICE probes it post-perihelion in November, we'll know more. But for now, it's a cliffhanger that demands you keep watching. These anomalies aren't isolated. They're a triad painting 3IATLAS as an outlier among outliers. CO2 flipping the sublimation script, nickel standing solo in defiance of stellar bonds, trajectory wiggles hinting at hidden hands. Together, they suggest formation in a system unlike ours, perhaps around a carbon-oxygen star in a metal-fractionated disk. Quantum AI's million-plus simulations converge on one theme. This isn't our comet. It's a foreigner, carrying blueprints from a stellar lab we can barely imagine. And as NASA's Quail team refines their models, drawing on 2025's quantum leaps, like DOE's expanded quantum and space collaboration for sensing and networking, the predictions sharpen. By December, when it reemerges for post-perihelion views, we might have spectral maps of its full coma, unlocking even deeper secrets. But let's zoom out. Humanity's fascination with skyfallers isn't new. It's etched in our bones. The ancient Egyptians didn't just admire meteorites. They revered them as gifts from the gods, smelting sky iron into daggers for pharaohs. Tutankhamun's burial blade, analyzed in 2016, was 10% nickel iron from a meteorite impact basin, symbolizing divine power. Wait, nickel again? Coincidence? Babylonians logged green comets as war omens in cuneiform tablets, tracking tails like prophetic fingers. The Maya, with their dreadlocked Venus calendars, saw comets as feathered serpents, Kukulkan's kin, heralding cycles of creation and destruction, their math so precise it predicted eclipses centuries ahead. From Stonehenge's Heelstone aligning with solstice meteors, to Chinese annals recording the 44 BC comet that split the sky, cultures worldwide spun myths from these visitors. Warnings, weapons, wanderers. They built ziggurats as observatories, pyramids as star maps, sensing what we now quantify. These objects bridge worlds. Fast forward to 2025, and it's not priests parsing omens, but quantum machines decoding data. Yet the chill is the same, that primal unease of something vast watching back. 3I/ATLAS isn't a feathered serpent, it's a precise probe, its anomalies too neat for pure chaos. Our ancestors would have sacrificed to appease it. We're sacrificing sleep to understand it. And understanding means power. Who controls the quantum keys to these secrets? In 2025, the quantum race is white hot. NASA's Quail processes space data for U.S. primacy, but China's Mishis quantum satellite, launched in 2016 and upgraded last year, beams entangled photons for secure comms and remote sensing. Google's Willow chip, announced mid-year, claims 105-qubit supremacy, while IBM's Heron processor hits 133 qubits with error rates under 0.1%. Private players like Rigetti and IonQ are leasing cloud quantum time to Astro Consortia. The stakes? First to model interstellar chemistry owns the metallurgy revolution. Nickel-pure alloys for hypersonic craft, CO2-based fuels for Mars hops. Detection Tech 2, AI trained to spot hyperbolic intruders years out, turning defense into dominance. Data flows are siloed. NASA classifies until peer review. China's CNSA mirrors with state veils. Corporates auction access. If U.S. quantum nets crack 3IATLAS's propulsion hints first, it's a century of lead in space race 2.0. United front or zero-sum scramble. The choice shapes who explores, who defends, who lags. Imagine AI forecasting the next visitor's threat level, scout, debris, or harbinger, before telescopes confirm. That's not sci-fi, it's the horizon trained on today's data. Stepping back, these anomalies coalesce into a narrative of otherness. Individually explicable, CO2 from carbon stars, nickel from supernovae quirks, wiggles from jets. Together, they defy databases. Quantum AI's outputs, millions of paths, zero local origins. It's a fragment from a disrupted system, perhaps a rogue planet's ejecta, or a Dyson swarm's leavings, though that's speculation, grounded in Loeb's musings. And the mass? 33 billion tons suggests density anomalies, maybe a rocky metallic heart under ice. As Webb feeds daily terabytes, models evolve, confusion mounting. Is it a bug or feature? What if 3I heralds more? 4th, 10th visitors, a stream we missed. If 3 in 8 years, projections hit dozens by 2030, per LSST surveys. Quantum AI now fingerprints 3I's spectra, ready to match kin. Scout or shard, debris from catastrophe or deliberate dispatch? Simulations can't say, but they learn. Pattern matching for the unnatural. When next arrives, decoding's instant, ready or not. For millennia, myths tamed skies. Now quantum spawns myriad truths, deepening enigma. 3IATLAS lingers months more, visible till December, then fades to void. But its echo endures in databases, awaiting matches. A star-born comet, AI probed, rule breaker. Webb watches, AI learns, Cosmos surprises. Follow for developments, subscribe, stay curious. Quantum's right, surprises abound.